Yes, hello. Class, is this audible?
Yes, ma'am. Good evening.
Good evening. So we had started with sharing of capacitors, grouping of capacitors in the previous class. And then we had seen there was loss of energy when we shared it and a common potential was also observed. The formula of common potential was C1V1 plus C2V2 by C1 plus C2. This was the common potential when two capacitors are connected. And then the loss of energy was this C1 C2 multiplied by V1 minus V2 whole square divided by 2 C1 plus C2. Okay, do one more question, one numerical. I'm writing down, just write yourself. Okay, now let's discuss it. So I hope you have seen the question once. So in this, what is there? Two conducting spheres are connected by means of some wire. Radius of the first sphere is R1, charge is Q1. Radius of second sphere is R2 and the charge is Q2. It has asked you to take out the ratio of the charges and the surface charge densities. Firstly, you have to calculate the charges, and with the help of charges, you have to find out the surface charge density. So in the previous class, we have only seen this topic, sharing of conductors or capacitors. Even if you share capacitors or even if you share conductors, the principle remains same. If you connect both of them, charges flow. So what is the direction of flow of charge? If I tell you both of them have certain potential, what will be the direction of flow of charge? Higher potential to lower potential or lower potential to higher potential?
Higher to low.
Higher to lower. Atif, till when will the charges keep on flowing?
Until both have the same potential.
Till both have the same potential. Very nice. So see, with the help of that concept only we will solve, which Atif has mentioned right now. When the potentials have become equal, potential of sphere 1, this is equal to the potential of sphere 2. This is the basis of your answer. This is how you will be starting with your answers. Because see, until both of them acquire the same potential, charges will keep on moving. Now you have to find out the ratio of charge. Fatima, you tell me. This is the sphere, radius is R1, charge is Q1. What will be the potential of the sphere? Yes, Fatima. For a point charge, or if you have a sphere, you have a formula, no, for potential.
K Q1 Q2 by R.
K Q1 by R1. See, potential's formula is KQ by R. So if you have Q1 R1, that becomes K Q1 divided by R1. Now, Fatima, tell it for the second sphere.
K Q2 by R2.
KQ2 by R2. See, constant, that is 1 over 4 pi epsilon naught, or even if I write it as K, it will get cancelled. And I want the ratio of the charges, means Q1 by Q2. See, Q1 by Q2 is coming what? This is coming R1 divided by R2. So this is your final answer. Akifa, please tell us what is meant by surface charge density.
Charge over
Surface,
area.
correct, charge over area. So see, for finding out surface charge density, it is better, no, we have charge with us. And see, the way Akifa has mentioned, it is charge divided per unit area. So if it is charge divided per area, so what if I divide it by all the charges? This will be Q2, Q1 by Q2. So what if I divide it by all the charges? If I have Q1 with me, I have Q1 with me. This was Q2, this was equal to R1, this was equal to R2. If I divide each term by area, there won't be any effect on my answer. It's just that I'll be getting Q1 by A and Q2 by A as what? Sigma 1 by sigma 2. This is what is the definition of sigma 1 and sigma 2. So this will be sigma 1 divided by sigma 2 R1. So you can place it as 4 pi R1 square, area of the first sphere, divided by 4 pi R2 square divided by R2. Means the R2 divided by area of the second sphere. So 4 pi gets cancelled, R1 cancels the square, R2 also cancels the square, sigma 1 divided by sigma 2 is R2 divided by R1. Clear? So write down the question as well as the solution. Done?
Yes, ma'am.
Alright. Now see a few important points regarding capacitors. So you can write it in the form of note only. These are some very important points. These will help you in your numericals as well as in your theoretical questions as well. See, when we have two parallel plates kept, air is filled in between them. Let's say we have connected it to a cell. The area of the plate is A, separation between the plates. This is D. So yes, Hanifa, tell us what is the capacitance of this? A is the area, D is the separation. So capacitance will be
A epsilon naught by
A epsilon naught divided by D. This is A epsilon naught divided by D. Correct. So that will be the capacitance. So this is which case. Let's say the potential is V naught. So firstly, we have taken parallel plate capacitor with air filled between the plates, with air filled between the plates and connected to a cell of potential difference. This is V naught. Now this is the basis of it. This is the initial case. General case, what is that? This is the general case. Air is usually filled, so it has some capacitance. Separation is D. So as rightly answered by Hanifa, this will be epsilon naught A divided by D. Let's say this is C naught. C naught, this is the initial capacitance. Initial capacitance means when this is filled with air and the battery is connected. This is the case. So C naught, this is epsilon naught A by D. Then charge will be what? Capacitance formula. Hiba, you tell us what is the formula of capacitance? When we had started with capacitance, we had seen a formula, no? What is that formula of capacitance?
Q by V.
Q by V, correct. This is Q by V. So see, so Q will be what? Q will directly be C naught V naught, because capacitance is Q by V, so charge will be C naught V naught. And third, we'll find four things. Potential difference, this is V naught, and electric field is V naught divided by D. If you remember this relation, we had done a relation minus dV by dr. Do you remember this? We had done this variation of electric field with potential gradient. So this is the general case that happens. Now modifications will occur and we have to relate it with the modification. Let's say this is the parallel plate capacitor. K is the dielectric constant and dielectric has been filling it completely. We have connected it, means that capacitor has been connected to the battery. Potential will be something. Now see, which is this case? Battery remains connected. This is important. Battery remains connected. And now we don't have air. The space, this is filled. This is filled with dielectric constant. Now we'll be relating all the four quantities. So regarding capacitance, as I've told you, whenever you have a dielectric slab continuously filling it, capacitance becomes what? Anyone?
K epsilon naught A by D.
K epsilon naught A by D. So the first quantity, capacitance, will be what? Let's say this is C, this will be K epsilon naught A by D. So epsilon naught A by D was C naught only. So this becomes K C naught. So see, we are multiplying C naught by something. We are multiplying the C naught by K. It means this is increasing. So if this dielectric slab is introduced, your capacitance increases when the battery remains connected. This is also important, when the battery remains connected. Now, charge is again CV. So this will be K times C naught, because capacitance is now K C naught, and potential difference, this is V naught. So C naught V naught, this is again charge that we had seen, K times Q naught. So as you can see, since this is K C naught V naught, charge is also getting increased. This also increases. Reason? Something is getting multiplied. So obviously the amount will increase. But this is the important point, most important point. When battery remains connected, always remember that the potential difference remains the same. Potential difference, this remains constant. So if potential difference remains constant, then your electric field will also be constant. This will be V by D. V is still V naught, there is no change in potential. V naught by D, this will be the electric field. So this also remains constant. But now, if I take the same case, I have a capacitor with me. Dielectric slab is completely filling it. I have this circuit with me, but somehow I disconnect this circuit. There's a barrier which you can see. I have disconnected this circuit in between. Potential is V, let's say. This is the dielectric constant, but I have disconnected it. Which is this case? Battery is now disconnected. And again, the space is filled with dielectric constant. It's filled with dielectric constant K. Now all the four things. Regarding capacitance, see capacitance, let's say this, all these things we'll be adding this prime symbol to show this is the new case when the battery is disconnected. See, this is important. Battery is now disconnected. C prime will definitely be K C naught, because capacitance will still be no K epsilon naught A by D. So your capacitance will be K C naught. So capacitance still increases. So even if your battery remains connected, if your battery is disconnected, your capacitance always increases in both the cases. Why? Because it multiplies and it becomes the times of the dielectric constant. Regarding the charge, now this becomes important in this. Charge remains the same. Whenever your battery is disconnected, charge remains the same. What about potential difference? See, potential difference, this is, let's say, this is Q prime. So V prime will be Q prime divided by C prime. So Q is remaining the same. C is K times C naught. See, Q naught by C naught is our original. V naught. Now your potential is getting divided by something. Here the capacitance got multiplied, so increased. Here your potential is getting divided. So it will increase or decrease?
Decrease.
It will decrease. Yes, it will decrease. And similarly, predicting electric field is very easy. See, E prime will be V prime divided by D. V prime is V naught by K. This is D. And V naught by D was the initial electric field when air was filled. So this also decreases. So these are all the 4 points that you have to remember. When the parallel plate capacitor was filled with air, when you had no dielectric constant, battery was also connected, these were the 4 things. But if battery got connected, capacitance and charge increased, potential and electric field remained the same. When capacitor got disconnected, battery is disconnected with the capacitor, capacitance increases, charge remains the same this time, and potential and electric field decreases. Clear? Is it clear to all of you?
Yes.
All right. So done?
Yes, ma'am.
So now see the last topic that is left is your series and parallel combination of capacitors. So see, we'll be doing it in this chapter only, but the whole thing will be getting repeated for your resistors in current electricity, which we'll be starting soon. So in current electricity, everything gets replaced by current, where you will be using electric charge here, it will be electric current over there. So we'll also study combination of parallel and series connections of resistors over there. So it's better you understand first how to check whether anything is in series or anything is in parallel. But before that, first understand how to check division of charge and potential. Because see, many a times you will be getting such a circuit where you won't be able to identify whether it is connected in series or is it connected in parallel, or sometimes it is neither connected in series nor parallel. So there you have to understand, are the charges equal or are the potentials equal? So without understanding division of charge and potential, you won't be able to understand. And see, I'm repeating again, this whole thing will get repeated for your resistors in case of current electricity. Now, first, let us discuss division of charges. Now, if you have a straight wire, then the charge remains the same in the wire, means the wire will be having the same charge flowing. Even if I bend this wire in this form, let's say in this form, I've bent this wire, the same wire. Q charge is flowing, this will keep on flowing, and here also this will be the same. So the same charge will be there. The charge has not divided yet. So how does the charge divide? Charge always divides due to branching. See, whatever you're studying for charge, you will be studying it for current. So charges divide by branching. Charges divide by branching. For example, here we had a straight single wire. Now this is wire, it has divided into two equal parts. Let's say not even equal. We don't know whether it is equal or it is unequal. This is capital Q. This is coming. This part is branching. Branching has occurred in the wire. Now the same charge cannot flow in both the wires. So it will divide into, let's say, Q1, and in this wire it has divided into Q2. If you add both of them, Q1 plus Q2, you will be getting Q back. But charge has divided at the junction. Now see, if you add any barrier, let's say one capacitor has been added, another capacitor has been added, then here also we have added a capacitor. In this branch also we have added a capacitor. Let's say this is C1, this is C2, this is C3, this is C4. All these are capacitors. Now the charges has started flowing. This is capital Q. See, all these capacitors, or in case of current electricity, you will be studying resistors. These do not hinder the charge. They do not interfere with the flow of charges. Until and unless the wire is same, the wire remains the same, the charges keep on flowing continuously. So capital Q is the charge flowing. It will still be capital Q only from this wire. At this point also it will be capital Q because this is the same wire. But see, over here you are able to observe that branching has occurred. It means now the charges won't remain the same. Let's say it has divided into some Q3. This was Q2 and Q2. Let's say this is Q3. And this has divided into Q4. Now this capacitor won't affect this Q3. See, you won't be getting capital Q, but whatever current is flowing in this wire, this is the new wire now. It has branched. So this will be Q3. Similarly, this point is point of branching. This will be capital Q4. This is how you see division of charges. Now, in case of potential, if you have to check for division of potential. Now in this case, this potential, this divides due to the capacitor. So in case of current electricity, if you have resistors, then resistor will be dividing the potential. So at the end of both the lessons, you will be able to connect both of them. Now, if you have a straight wire, this is a single wire. This is a straight single wire. So if you have a wire with you, this is the same wire. So let's say at point A, this is some point B, this is some point C. All the potentials will be equal because it's the same wire. Even if I bend this wire, this is that point A, this is now B, this is point C. Same wire, I've bent it from here. Again, VA, VB, VC will be equal. But if I add a capacitor, there will be potential VA over here, there will be potential VB, and potential difference across the capacitor. This is V, this is given by VA minus VB. This is how you calculate the potential difference, because there is a potential difference now. Potential is not the same. If you have, for example, let's say, here the wire has divided. A capacitor has been added, here a capacitor has been added. Here the potential was V. Over this point, potential will be V. See, branching does not affect your voltage. So here also it will be V. Let's say this is VA. At this point also it will be VA. But since a capacitor has been added, this will be something else, VB. A capacitor, another capacitor has been added. This will be some another point, VC. Clear to all of you? Are you able to relate this? How to differentiate between division of charge and division of voltage?
Yes, ma'am.
What about others? Akifa, Fatima, Hamza, Huzaifa?
Can you repeat once more?
Yes. See, because this is the basic, without this, you won't be able to even identify whether the circuits are connected in series or parallel. If you see any branching, no, whether the wire has been
These are
divided
only for
into three
potential,
branches.
not for charge. Only for
Okay,
potential.
okay, only for potential. So for charges, if you see branching, charges get divided. In case of potential, if you see a capacitor, that hinders your potential. Means at one end of the capacitor's plate, there will be some potential. At the end of the other plate of capacitor, there will be another potential. If even though this is the same wire, the potential gets changed. So difference, if you are asked to calculate the difference between what is the potential difference across the capacitor, since you are getting two different potentials, you can take the difference of them and get the potential. In this circuit which we were discussing, in this what is happening? See, this is a continuous wire, it has divided. Now branching has no effect on potential. Branching does not affect potential. So if it was VA, it will still be VA till the time you are not able to observe any hindrance, blockage like capacitor, any device like inductor or resistor. Potential will be the same throughout. As soon as you see a capacitor, potential gets changed. As soon as you another capacitor, the potential gets changed. Now difference in this will be given by VB minus VA, or whatever is the sign according to the sign, VC minus VA. Clear now? Yes,
Yes.
Atif? Any doubts to anyone? All right. If you have any doubts, you can ask me. Start noting it down. If you get stuck, just ask me. Because if you understand this, then identification of series is very easy. Charge remains the same, so you get series combination. Potential remains same, so you get parallel combination. And then you have the formula once you identify it as series or parallel.
Teacher, does the charges divide equally or will there be an unequal distribution?
It can depend. It depends. It depends. It
Okay.
doesn't matter. Charges can divide equally, they can divide unequally. And it doesn't even matter how much the branching is occurring. If it is two, like this wire has divided into two parts, so it doesn't matter that the charges will be equal. All right. It will depend on the situation.
Okay.
See, now let's start with series combination of capacitors. So in this, now it will become easier for you. The main part was what we have studied just above this. Charges remain the same, where potential remains same, where charges get divided, where does the potential get divided. Now see, in case of series combination, let's say there are 3 capacitors. Or let's take n number of capacitors. Directly let us formulate the general formula. So this is C1, C2 and up till Cn, these are connected having the potential V. So remember, in series combination, whenever you have to identify, if you see such kind of circuits, these are very simple, easy circuits. First, we'll be starting with easy circuits only in today's class. Then we'll see how complicated circuits can be solved. When you have potential divider method, that we'll also see. Because sometimes just by looking at the figure, you will not be able to identify whether it is series combination or is it parallel combination. So in series combination, charge stored in each capacitor. This is important. The charge stored in each capacitor, this remains the same. Charge stored in each capacitor, this remains the same. Is same while potential divides. So you can relate it also. See, this is the same wire connected in this circuit. So obviously the same charge will flow in this capital Q, let's say. And since these are different capacitors, so there will be different potential at either sides of the capacitor. So whenever you see such a combination where the charges are same, quickly identify that it is series. Don't go by the figure. That this is looking like that is connected in series or something. Let's say this is C equivalent. Means all the net capacitance we are considering, which is connected, means all of these are connected in series. Cn, we have to find out C equivalent. Charge is capital Q, potential is V. See, potential, total potential difference is what? V. This is the total potential difference. Net potential difference will be what? V1 means potential difference of first capacitor plus potential of second capacitor plus potential of third up till potential of nth capacitor. In terms of charge and capacitance, if I write this, so potential will be charged by capacitance. So this will be Q divided by C equivalent. Net charge, the whole charge of the system divided by the whole capacitance, which will be equal to what? V1 means charge of the first one divided by the capacitance of the first one. Why are we not writing Q1? Because charges are not different. Charges across each capacitor is same. So even if you write Q1 or you write Q2, all of them Q1 will be equal to Q2 only. Plus Q again will be the same because it is connected in series divided by C2. Up till when? Charged divided Cn. See, all the charges get cancelled. Your C equivalent is given by 1 by C1 plus 1 by C2 up till 1 by Cn. This is the formula of series combination of capacitors. That's how you calculate. See, when you will be doing resistance, no resistors, it will be the opposite. Whatever is the answer of series combination of capacitor becomes the parallel combination of resistors. But you will be able to analyze it that time when we'll be doing it. Right now, just focus on capacitance. So this is the net capacitance that is calculated. Now see, if this is the net capacitance, net charge can be written as C equivalent divided by V. Can be the charge of the system. If you are given the C equivalent, if you are able to find out the C equivalent, if you know the potential difference of the whole cell that is generated, you will be able to calculate the net charge also. But if you are asked to calculate the potential difference across each capacitor, then calculate it in this manner. V1 by V is equal to Q by C1, V2 is equal to Q by C2. So Vn will be what? Vn will be Q divided by Cn. Then calculate it in this manner if you are asked to calculate for each of them, if you have it for each of them. Similarly, all rest of the quantities as well. If you have energy, we talk about energy. It was in terms, let's say Q and C. It was Q square divided by 2C, if you remember, half Q square by C. So across individual, just calculate in this manner. Q square will be the same divided by 2C1. For U2, it will be Q square divided by 2C2. For UN, take charge square divided by 2Cn. See, are you able to observe? Charge is remaining the same. Only the capacitance is getting different. And if you are asked to find out the total energy, this is the individual energy of each capacitor, no? Capacitor 1, capacitor 2. If you have to find out the total energy, then you can add all of them or directly write Q square divided by 2 multiplied by C equivalent. Instead of writing C1, C2, take C equivalent. That's how you will get the total energy. So let's do a formula based question on it. Firstly, note down all the points of series, then we'll do a formula based question, easy question, so that this gets clear to all of you. See, all the formula, you have it in your notes. Two capacitors are there. You don't even have to convert it. They are in their SI units, 5 farad and 10 farad. Total potential, total voltage of the system, of the circuit, this is 10 volt. You have to first tell me what is C equivalent, total voltage, total charge. At least these three parts, all of you should try. C equivalent, you know the formula, 1 by C1 plus 1 by C2. Total voltage, just check what is the total voltage of circuit. If you know total voltage, if you know C equivalent, multiply it, you will get total charge. Then charge stored in each and voltage across each. At least first three part, everyone should submit their answers quickly. The calculations are also not tough. And you can leave it in the form of fraction. No need to solve it in the form of decimals. But at least solve it quickly and submit your answers, all of you. Yes, answers of the first part. 5 farad, 10 farad, take this equivalent. Very nice, Atif. So Atif has solved all the first three parts. All the answers are correct. Atif, try the fourth and fifth part also. You'll be able to do it. Fatima, something is left. I think some typing error is there. Just check your answer for the first part. What about others? Hurry up, quickly submit your answers. Krishna, Huzefa, Akifa, Rishan. Okay, all those who have got the answer of the first part, tell it for the second. In the second one, you don't even have to calculate anything. Hamza, use that formula. 1 by C equivalent is equal to 1 by C1 plus 1 by C2. Fatma's second answer is correct. First is not correct. Just check it for the first one. Second one is correct. Others also submit your answers. This is a very easy question. Very few students have submitted. Only Fatima, Hamza, and Atif. Only these three have tried. Okay, Hanifa has also got her answer. Very good, Krishna. So Krishna has solved it till fourth part. Krishna, try the fifth part as well. You will be able to do. Hanifa, I think you have got 1 by C equivalent. What will be C equivalent? The answer that you have got, that is C equivalent not. That is 1 by C equivalent. You have to tell me what is C equivalent. See, this is a very easy circuit. You will be getting complex circuit. Complicated circuits will be there where even identification of series and parallel will be difficult. This is just general formula based question. Let's discuss it now. This was sufficient time given. Yes, Hamza. Now it's correct. Now it's correct. So C equivalent is what? C equivalent is basically 1 by C1 plus 1 by C2. 1 by C equivalent is 1 by 5 plus 1 by 10. See, multiply this by 2 and divide it by 2 because your LCM is 10. Your LCM is 10. You multiply this by 2. What is your V1 coming, Krishna? It's 2 volt.
Sorry, ma'am, it's 10.
Just check it once again. See, voltage won't be the same. Voltage will definitely be different because capacitors are there. So this will be 2 plus 1, that becomes 3 by 10. Now see, the mistake that you had committed, Hanifa, you had written 3 by 10. See, 3 by 10 is what? 3 by 10, this much farad is 1 by C equivalent. You have to find out C equivalent. So just reciprocate it. Don't forget this last step. If you do not take the reciprocal of it, you will be getting 1 by C equivalent. This much farad is your C equivalent. Is it clear? First part? Now see, second part says total voltage. Total voltage is given to you. Total voltage of the system is 10 volt. Voltage across each capacitor is not given to you. No, total voltage across the system is given, so you don't even need to calculate it. And third part says what? Charge. Now charge or total charge is what? Total capacitance multiplied by total potential. Total capacitance you have calculated 10 by 3. Total potential is 10. So this comes out to be 100 divided by 3 coulombs. This much answer. Now for the fourth part. Fourth part was asking you charges across each of them. In case of series combination, charges remain the same. So Q1 will be equal to Q2, which will be equal to 100 by 3 coulomb. See, this was a very easy question. Quickly, all your parts were getting solved. And the fifth part was voltage across each. So V1 will be charge divided by C1. This will be charge is 100 by 3. C1 is 5. So this becomes 20 divided by 3 volt. Similarly, V2 is charge divided by C2. This will be 100 by 3 divided by 10. This becomes 10 by 3. If you can even cross check it, see 20 by 3 plus 10 by 3, you should get the real voltage back. If you add 20 by 3 and 10 by 3, you get 10 volt back, which is the total voltage of the system. All right, so just note down the solution. If you are still not able to understand, ask me, because we'll be dealing with complicated circuits. You'll be getting circuits where infinite capacitors will be added. Sometimes identification of series and parallel will be difficult. So if you have any doubts, just ask me. Then let's start with parallel combination of this. Now, parallel combination, the way charge remains the same in series. Similarly, potential remains the same. So if you have parallel combination, let's say this wire has this capacitor, this wire has this capacitor, and this wire has this wire has divided into three parts, not equal, let's say 3 parts. So charge has flowed to it. So now charge distribution will be different. Now you understand, because charge gets divided by branching. And in parallel combination, you have branches only. But potential difference of the whole system, this will be the same. So in parallel combination, you have what? Voltage across each capacitor is same, while charge divides. Charge gets divided, but this remains same. So if let's say this is C1, C2, let's take it as Cn. This will be Qn. This is the voltage. Same voltage will be there in all these three. VV will be the same. Q is directly proportional to capacitance. Whatever will be the charge, this will definitely be proportional to capacitance. But C, what will be the equivalent capacitance? Charge is the same, so Q total charge will be charges are different, so net charge will be Q1 plus Q2 up till Qn. Q is equal to CV, so this will be C equivalent potential. This will be C1 multiplied by potential of the capacitor plus C2 multiplied by potential of capacitor till Cn multiplied by the potential of capacitance. See, voltages will get cancelled. C equivalent will be what? This will be C1 plus C2 up till Cn. So you just have to add them in case of parallel. So in case of capacitors, the parallel circuits are very easy because you just have to multiply them. If you multiply them directly, you get your net capacitance. Now, charge stored in each. Since charges are different, charge stored in one of them will be C1 multiplied by V1. Charge in the second one will be C2 by V. So directly we can write charge in nth will be C equivalent, not C equivalent, which is Cn. This will be Cn multiplied by V. Cn multiplied by V. This is how you calculate the charge. Josefa, you tell me how will I calculate the potential of each? Potential of each of them? Yes, Josefa, I'm waiting for your answer. How will you calculate potential of each? Fatima?
V is equal to Q1 by Cn.
Qn by Cn. See, Josefa, KQ by R is the potential for sphere or point charges if you have. But for parallel plate capacitors, you don't use this. All right. See, potential, you don't even have to calculate. Potential will be the same. V1 is equal to V2, which is V of the whole system. Potential is not getting changed. So same potential will run across all the capacitors. All right. So potential in all the wires, potential will be the same. Charge will be different. All right. So this will get clear through a question. Let me give you a question. An easy question I'm giving you right now, then we'll be dealing with combination. Right now we are dealing with only parallel. This is parallel circuit. 5 farad, take the same value, 10 farad. And the calculation is easier. Take it as 10 volt only. Now you have to calculate C equivalent, everyone should answer. You don't even need to calculate this. Total voltage, this is also very easy. First two parts, you can just answer by looking. Total charge, tell me voltage across each. Voltage across each of them. Then the charge in each. Charge in each, energy in each, and one more part, total energy. So first note down the points, then solve this. First note down the points for parallel combination. So in case of parallel combination, voltage across each will remain the same. Yes, Fatma, first, second parts answer are correct. So first, second, third, fourth parts, yes, they are correct, Fatma. Yes, yes, Hanifa, your first part is also right. Hanifa, try the second and third part as well. Others also respond who didn't answer the previous time. Akifa, Hiba, Huzefa. All right, so second part is correct, Hanifa. Second part is correct. Fatima, your fifth part is also correct. Try the sixth and seventh part. For seventh part, just add whatever energies you are getting for each of them. Atif, it is correct. Yes, yes. All the parts are correct, Atif. Atif, then try the energy portion. You can directly use half C1 V1 square for it. For one, you can take half C1 V1 square. Then for the second one, take half C2 V2 square. Add both of them to get the total energy for the seventh part. Yes, Hanifa, third part is also right. So only Hanifa, Atif, and Fatima. Only 3 students have answered. Rest of you, what about you? Are you people answering? Akifa, Akifa, the first answer. Is there a typing error or this is your answer?
Yes, ma'am, that's the answer.
Krishna, Huzefa, your answers. Hiba. Oh, Krishna has calculated all the parts. Yes, yes, correct. All the parts are correct. Yes, Atif, yours is also correct. This will be 750 joules. Yes, correct. Now let us discuss. So the third part, Akifa, your answer I've seen. That is correct. Okay, let's discuss it. Huzefa, you tell me, how do we write C equivalent for parallel combination? Huzefa Ahmed. Just now you must have done it. You must have written it down, no? C equivalent. Is it 1 by C1 plus 1 by C2 or is it C1 plus C2? Huzefa? C1 plus C2, correct? So why didn't you answer, Huzefa? See, C1 plus C2 is what? This is 5 plus 10. This is 15 only, 15 farad. So easy. Second part says total voltage. Total voltage will be 10 volt. Total charge. Total charge is what? Total capacitance multiplied by total voltage. So this is 15 multiplied by 10, which is 150 coulombs. All of you, when you're answering, do add the SI units. Most of you have written with the SI unit only. For those who didn't write the SI unit, always mention the SI units because you hardly get the capacitance like this in terms of farad. Most times you get it in terms of microfarad or nanofarad. So it's better you write in terms of the SI unit. The fourth part. Fourth part says what? Voltage across each. In parallel combination, voltage does not get changed because from here also you have the same voltage. From here also you have the same voltage. So voltage will be the same. So V1 is equal to V2. This is equal to 10 volts. See, does not even take this much time. Since I'm discussing and repeating things, that's why it is taking time. This question will just take you 2 to 3 minutes. Then fifth part, charge in each of them. So you can now say C1 multiplied by V. So this will be C1 is what? 5 multiplied by V. This is 50 coulombs. Q2 will be what? C2 multiplied by V. Capacitance 2, this is 50 multiplied by 10. This is 150 coulombs. This is how you get. This was 15. This is 10. 10. Okay, this is 10. So this will be 100. This is 10 farad. No, so this will be 100 coulombs. You will get 100 coulombs. Sixth part says what? Energy in each of them. See, for the calculation of energy, you can directly use the formula half C1 V1 square. If you know half C1 V1 square, you can finally directly find out the energy. So see, energy will be what? U1 will be half C1 V square, half C1. Let's say this is 5 V square. This will be 100. So this will be 500 by 2, that is 250 joules. U2 will be half C2 V square. This will be what? Half. This is 10 into 100. This is V square will be 100, no? So this becomes 1000 by 2, that is 500 joules. If you have to find out total energy of the system, add all the energies U1 plus U2. You get 250 plus 500, which is 750 joules. I hope it is clear to the rest of the people who didn't answer. Is this clear?
Yes.
Oh. So just note down the solution, all those who have not written, and we'll do one last question for today. The complicated circuits we'll be dealing in the last class of this. We'll take one more class of capacitors, just how to solve the circuits. Different methods are there. Not only this method, this is formula based, this is the first method. You have various methods to solve them. You also get a condition where a Wheatstone bridge is formed. That also we'll be studying here. So all this will become easier when you'll be studying resistors. So understand it well in this chapter. One more circuit I'll be giving you. So all those who will be able to solve it, please try. It's an easy circuit. Today I'm just giving you all the easy circuits. This was just formula based. Now the SI unit, this is farad. SI unit of capacitance is always farad. So now the unit that I'm giving, this is microfarad. So do convert if required. If you see all of them are in the same, then no need for conversion. You can leave the equivalent capacitance in terms of microfarad only. C equivalent total voltage total charge. These are the three capacitors. So you just have to identify which are in series, which are in parallel. If parallel combinations get reduced, what will, if whether they'll be now in series? Just check it. Take 2 minutes, then I'll discuss this. Very nice, Akifa. Correct answer, and so quickly. Others also, please try. At least equivalent you should be able to tell. Akifa, you try the second part as well, second and third part as well. You'll be able to answer. Second part is total voltage across the circuit. So no need of calculation. Third part you should try. Yes, yes. Second part is 10 volt only. 10 voltage is the total voltage of circuit. Others tell at least equivalent. Yes, Atif, correct. C equivalent is correct. Hamza, Hanifa, Hiba, Huzefa, you also try for the combination. Okay, Akifa, correct, correct. Akifa, this is the answer of the third part which you have submitted.
Yes, ma'am.
See, once again, you're getting C equivalent. You know the total voltage. Will this be the answer? All the three parts are correct, Krishna. Yes, Atif. Second's answer will be 10. Okay, let's discuss it now. Do you need some more time, others, or should we discuss it now? Okay, take a minute. Okay, take a minute. Yes, Akifa. Now your third part is correct. See, if you are able to identify both of these are connected in parallel. So let's first solve these. These means what? Let's say this is C1, this is C2, this is C3. C2 and C3. These are connected in parallel to each other. Are you able to identify both of these are connected parallel to each other? Now, equivalent capacitance in case of parallel combination. This is simply by addition of it. So this will be C2 plus C3. This is how you get parallel combination. So C2 is 5 microfarad plus 10 microfarad. That gives you 15 microfarad. It means I have reduced this system into C23. I have got a single capacitor. See, how can I write this? Now I can write this as, this circuit as, see, 10 volt will be the same. 10 microfarad will be the same because we haven't disturbed it. But regarding these two we have solved it in the form of a single capacitor, which is C23. C1 is there. C23 has been reduced. We have reduced it to a single capacitor. The combination, we have found this equivalent capacitor and we have reduced it. And this is how now your circuit looks like. When you have taken the parallel combination, this is now how your circuit looks like. This is C23. This is how you see it. Even if you get reversed question, then you should be able to expand it. All right. Now see, C23 means this combination is connected in series with C1. These are connected in series. So how do you get the C equivalent of the whole system? That will be 1 by C1 plus 1 by C23. This is how you write the net capacitance of the system. Why? Reason is that because both of these are connected in series. Now you just have to put in the values. One you are getting 10 microvolt, other one you have it as 15 microfarad. So this will be 1 by C equivalent. 1 by C equivalent will be 1 by 10 plus 1 by 15. So take the LCM as 150. This will be 10, this will be 25. Here you will have 25. You multiply it with 10. This will be 25 and you multiply it by 15. Now C equivalent is what? C equivalent will be reciprocal of it. 150 divided by 25. So this becomes what? This comes out to be 6 and the SI unit is farad, but no need to write it. You can leave it in terms of 6 microfarad. If needed, you can then convert it 6 into 10 to the power minus 6 farad. This is your capacitance. Answer for the first part. You have to find out the net capacitance in this manner only. How to find out the net capacitance? See, first try to reduce the circuit. See, if you see this capacitor C1, had we tried something else, C1 and C2, see, you are not able to observe it. This is neither in series nor in parallel. C1, C3, both of them are not connected together. It means neither in series nor parallel. But you are able to identify C2 and C3 are definitely connected in parallel. You can see branching. This is how parallel combination is made. So since we know the formula of parallel combination, we can easily reduce this. Now, once you have this combination, now check. Now we are able to see C1 and C23, both of these are definitely connected in series. So we were able to solve the further parts. Regarding the second answer, total voltage will be the 10 volt only. This is the total voltage of circuit. Third part says total charge. Total charge will be what? Total capacitance multiplied by total voltage. That's how we have been calculating. C equivalent, this is 60 microfarad. Voltage is 10 volts. So Q becomes 60 microcoulomb. This is 6 microfarad. No, this is 10 volts. So your answer, this becomes 60 microcoulomb. That's why I was constantly telling you all, write down the SI units. Because if you omit the SI unit, your answer directly comes out to be coulomb. So some of you had mentioned it. Krishna was correct. I think Krishna was right. Someone else was also correct. So because if you mention the the units, you will be able to understand this is not an SI unit. It is coming 60 microcoulomb. 60 microcoulomb is different from 60 coulombs. If you don't write the unit, if you don't focus it on the unit, so either you can convert it in this manner, or you can write it 6 into 10 to the power minus 5 coulomb. That correct. All right. So quickly copy it down. All those who are not. Done? All those who have written, just write me done in the chat box. Okay, so most of you have completed it. All right. So I'm stopping here today. Just revise all these basic circuits. In the next class, we'll be having the last class for this chapter. Then we'll start with current electricity. In the next class, we'll be studying the combination of series and parallel. We'll be using both of them and seeing different methods. All right. So if you have any doubts, you can ask me. Otherwise, then let's meet in the next class. Okay. No. Bye bye.
Thank you, ma'am.
Thank you, teacher.